This is a lesson on refraction and thin lenses in the unit on light and optics. In a prior lesson, I covered mirrors, and also in a prior lesson, I covered refraction. And what we're going to do is combine those ideas that when light goes through a medium, I can use it in order to create an optical instrument. So with thin lenses, what we have is a piece of refractive material characterized by a focal length. We're going to use a lens very thin in the middle. That's why I'm calling thin lenses. Thick lenses, this won't happen for. But thin lenses, and the two sides of that lens are symmetric with one another. What we see is when that is true, when the shape of that lens is like that, all incoming parallel rays will pass through what we call the focus, the focal length. So if I have light coming from the sun, which is infinitely far away, all of those light rays will be coming in parallel, get captured by what I have here, a magnifying glass, and all of those light rays will pass through the focus. And so to emphasize that point, we can get all of that energy. All of these light rays are separate at that point before then, but at that point we can get all of the energy of all those light rays focused at one point, and you can start a fire, for instance, with that. The law of reflection applies at the two surfaces. So when we're looking at a lens, there's definitely two sides here, and the law of refraction will happen at the first interface, and it will happen at the second interface. You will never have to do the math in order to figure out the angles of direction. What we do is the same thing as with mirrors. We do ray tracing, and we know certain rays follow certain paths. You will not have to do the calculations on following the rays through a lens. There are two different types of thin lenses. The first is converging, the second is diverging. Converging lenses, outgoing rays converge at the opposite focus. So if we have a bunch of rays coming in parallel, and please forgive this diagram, I reversed it than what it was in the book because they had the light going from right to left rather than left to right. So we're following the light from left to right in here. The light comes, hits halfway through the lens, and I recommend that wherever you see a lens, just draw a line halfway through. And at that point, instead of having the light refracting at two different surfaces, just redirect it at the middle of that lens. And so we can see light comes in, gets redirected by the lens, and all light coming in parallel for a converging lens comes in, and it focuses, it converges at that focus. The diverging lens, what we see is the outgoing rays never meet up. They diverge out here. So we have the same rays coming in parallel, right? But what they do is they diverge on the other side rather than converging. And all of these light rays, as they diverge on the other side, they appear as if they originated at the focus. One last thing I'm going to note, because I think these pictures are deceiving. Each type of thin lens has two foci, all right? They only have one drawn in here. So here's one, but I would say there's another one back here. Here's one, but there would be another one on this side as well. All thin lenses has two foci. Another thing to note is a higher index of refraction affects light more. So if you have a higher index of refraction, if I make this a more dense material, its focus, its focal length will decrease. It'll become smaller. If the end becomes bigger, then you have a smaller focal length. It bends that light more. It has more capacity to bend the light, and so that focal length will become shorter. A property of lenses is to have a power. The power of a lens is measured in diopters, and it's very easy to calculate. It's one of the few easy equations in physics. The power of a lens, P, is 1 over the focal length in meters, and that's measured in diopters, D. Notice this does not have to do anything with energy. There's no joules in here. I'm not measuring an amount of energy or work or anything like that. This is a power of a lens, its ability to bend light. The smaller focal length corresponds to a larger power. It has more power to bend that light. So that's the properties of thin lenses. We can use them to create images of objects. That's typically what we use lenses for, is to apply them. So when we look at image location and ray tracing, we did this with mirrors, and you can go back and look at those for mirrors. The rays that we trace for mirrors are very similar to the rays that we trace for lenses. And I put the three of them here. There's three principal rays. There's three principal rays for mirrors. There's three principal rays for lenses. When we look at the two different lenses, because the foci, the light either converges or diverges, we have to think about the principal rays differently, and that's why I'm doing the converging ray first. The first ray that's easiest to draw is to draw a light ray coming in parallel to the central axis, and what we know is that it will go out through the focal point. Again, draw a line through the middle of the lens and just redirect the light at the middle of the lens. The book gets technical here with doing some refraction at the front and back of the lens. I don't recommend doing that. When you're doing your drawings, and I'm going to do an example of this, just draw a straight line down the middle and redirect the light at that line and have only two rays that you're drawing. So this one comes in parallel, leaves through the focus. The second one here, which is really easy to draw, and is the third one in the list compared to when we looked at mirrors, is it goes in and out through the center of the lens. And because this is light, it goes through the lens, okay? So it's going to go through the center of the lens, where the center of the lens meets up with the central axis. And that's a very, very simple line to draw. The last one here, the third one, which is the second one compared to the mirrors, is that the light goes in as if it were going through the focus. We line up the light with the focus, and notice that this is the other focus. And I put that in here, the other focus. If you use if you used one focus for the parallel light, you're going to use the other focus for this last ray. So you send the light in through the focus, it hits midway through that lens, and it will go out parallel. So it is sort of the opposite of one. This goes in at parallel, out through the focus. This goes in through the focus and out parallel, but it's through the other focus. Make sure you're using the two different foci here. So when we add all this together, when we have ray 1, ray 2, and ray 3 going through a converging lens, notice that they all go through that lens and they end up on the other side, and this creates an image. This is a real image. If you remember from mirrors with virtual and real, this is a real image. The real light rays actually converge together to create this image. This is an image that you may project up onto a movie screen if you have a slide projector, etc. Ray tracing with the diverging lens is a little different, again, because the focus is a negative value rather than a positive value, so we have to take that into account. I have two here. One, the first ray that you draw will go in parallel to the central axis. That's the same as converging lenses, but we can see here it doesn't converge on this side, it diverges on that side. So I recommend draw a line halfway through that lens and redirect it as if it came from the focus on this side. The second ray is just going through the center of the lens, where the center of the lens meets the central axis. The third ray that we would draw is the ray that would go in, and I have this down here. You can see the purple ray down here, number 3, the purple ray down here. The purple ray heads into the lens as if it were going to the other focus. Notice on the first ray, I went in parallel and already used the focus on the same side. Now I'm going through the other focus, I'm going to make it look like as if it's going into the other focus, and then it gets redirected at the middle of the lens to go out parallel to the central axis. That's the ray that gets extended back behind the lens, and that's what forms the image. I'm going to note here that this is a virtual image. They noted that here. Another thing that I'm going to take a moment to really highlight is with mirrors, like if this was a mirror, students like to think that there's a positive side and a negative side, and that works for mirrors. But in this instance, it does not work for lenses. This is the positive side for an object. This over here would be the positive side for an image. The positive is always where the real light goes. So I can see that the positive image distance is going to be over on this side. That's over on this side. This is a real image. This will get a positive image distance. Because this is a virtual image, it will get a negative image distance. And that's true for mirrors, right? Whenever there was a virtual image, it will have a negative image distance. That's true for lenses as well. But remember that it will be on the same side as the original light. Virtual images are the extensions of the real light rays behind that device. So watch your equation when you're determining these values for object and image distances, what positive and negative, where that is. We're going to use the mirror lens equation, which we saw in mirrors before, 1 over f equals 1 over do plus 1 over di. And so that's the object distance, the image distance, and the focal length. You will need to remember to use positive and negative focal length. A positive focal length is for the converging, and a negative focal length is for the diverging. So watch out when you're using this equation, you have the right signs. Magnification of an image is given by the same equation that we use for spherical mirrors, negative di over do, and the original definition, the ratio of the image height over the object height. I chose a problem here that is familiar, and I like it because it gives us a virtual image. And it's a magnifying glass. I don't know if you have a magnifying glass, if you've used magnifying glasses before. We're going to take something that's small and make a larger image of it. And it will be an upright image. If I use a magnifying glass to read a sheet of paper, I don't have to turn it upside down or anything. It will be an upright image as well. So let's see what this problem's saying. It says, suppose an object such as a book page is held 7.5 centimeters from a converging lens of focal length 10 centimeters. So I'm getting a picture here in my head. What I'm going to do is draw a central axis. And this is a converging lens, so I can draw a converging lens. I'm going to make it kind of big here across the axis. And then it's not symmetric. It's not perfect, so what I'm going to do is just draw that line down the center there, and that's where I'm going to redirect my ray tracing, the principal rays. I'm going to note that this is a positive focal length, and it is a positive 10 centimeters. What I do is I draw the two focal points in here, 10 centimeters one way, 10 centimeters the other way. Remember, thin lenses have two foci. You can call this F1 and F2, whatever you want to do there. I don't label them differently. I keep track of them. Let's put an object in here. Here is the book page, and it is 7.5 centimeters away from that lens. All of the image distances and object distances are measured from the center of the lens. So it's held 7.5 centimeters from a converging lens with a focal length. So this object is within the focal length. And so this is what we're going to do, is include a ray tracing sketch to verify any of the mathematics the calculations I do here. So I'm going to draw the three principal rays for you in this situation. There's a ray that goes in parallel to the central axis. I'll put a line on that. And then, because it is a converging lens, that ray will go out through the focus. So I'm going to create a line that goes through the focus, and it originated at that halfway point in the lens where the original ray hit the lens midway through. So I'm going to put that in here. And I extended it backwards because I expect a virtual image. And we're going to see that in a second. Okay, so we see that the ray is going to head out in that direction, and this is the extension of the ray behind the lens. Let's draw another ray. Another ray will be very easy to draw. Let's draw it through the center of the lens. We'll draw it through the center of the lens, and I'm going to line up the center of the lens with the tip of my object, and I'm going to extend it backwards here behind the lens, and we can see that they're going to meet up back here. The ray will continue forward, and what we're seeing is that the ray does, these two rays that I just drew, they do not meet together on this side of the lens. They actually converge on the back side. And so these are the extensions of the light rays behind the lens. And so what we're going to note is that this is a virtual image. I'm going to expect my image distance to be negative. I'm going to expect a positive magnification. And I can see that it's a larger image, which is what I expected, right? It's a magnifying glass. I expected to magnify to make larger that original object. So this is a ray tracing. Let's do one more. One more would look like this. I would line up the focal point, the other focal point. Remember, I already used this one in my first ray. So I have to use the second focal point, and I would line it up with the tip of that object and make it head towards the lens halfway through. Once it gets there, what I'm going to do is send it out parallel to the central axis. So it's hitting right about here, and I can see when I extend it backward, it's not perfect. You won't always get this perfect, but the image where they converge is going to be about in the same area. So that light ray would go off in this direction, not converge with these, but I can extend it behind the lens. So let's do some math. Let's find the image distance. It says what magnification is produced. So I need the image distance in order to find the magnification. So the image is going to be 1 over f minus 1 over do, and then I have to invert that quantity. The focal length I know is 10. It's a positive 10. I'm going to subtract off the object distance, which is 7.5 centimeters. Again, I'm leaving this in centimeters. I have no preference to have an answer in meters. As long as they're in the same units, I can use this equation. And when you plug this through your calculator, you actually get a nice round negative 30 centimeters. And that makes sense to me. It's a negative value. I expected a negative value, and I can see it's about 3 times the way of the focal length from the lens. So now I can calculate the magnification, negative di over do. So I'm going to put negative of negative 30 over do is 7.5, and when you run this through, you get a magnification of 4. So the text on that book page is magnified 4 times larger. You would be able to read it better, and that's the point of a magnifying glass. So it's creating an enlarged image that is virtual and upright.